Let us discuss the transient analysis of discharging of a capacitor. In the circuit shown here, you can see there is a capacitor with charges plus Q and minus Q on the plates. With the resistance, it is connected in the circuit via switch. Say at t equal to 0, if we close down the switch, we have discussed that the charge will discharge through the resistance and a current flows. And as the value of R increases, the value of current will be lesser in that situation. And in a given situation, if it is discharging and at any instant the charge on plates are plus small q and minus small q, here we can write down the KVL equation for its analysis. If we write KVL equation for this loop in circuit, we can start say from this point, then moving along with the current. If we pass through the capacitor from negative plate to the positive plate, it will be a gain in potential, that will be plus Q by C, which is the potential difference across the capacitor. And through the resistance, when we pass, there will be a drop in potential, that is minus IR, which is equals to 0. So in this situation, you can see the value of current we are getting here is Q upon RC, and as with current, charge on capacitor plates are decreasing, we can write current as minus dq by dt, as dq by dt must be negative. So in this situation, we can see we have dq by dt is negative of q by rc, and if we separate the variables, we are getting dq by q is equals to dt upon rc with a negative sign. And if we integrate it on both the sides from 0 to t, and if we talk about the charge, initially at t equal to 0, charge was capital Q, and at time t it reduces to small q. On left hand side, after integrating, we are getting ln of q within limits from capital Q to small q, and on right hand side, integration of dt is t, so this is minus t by rc. So on substituting the limits, it will be ln of q minus ln of capital Q, that is ln of q by capital Q is equals to minus t by rc, and this implies if we solve for the charge on capacitor as a function of time, this will give us capital Q e to power minus t by rc. So this is the charge on capacitor as a function of time we are getting here. And if we plot the graph for this exponential function of charge as a function of time, you can see at t equal to 0, charge was q, and then it is exponentially dropping down, asymptotic with the time axis. And here you can see, if we talk about the time constant tau is equals to rc, then we can see the value of charge we are getting is q by e, that will be 0.37 of q. So we know time constant of a given RC circuit is RC. So at this time, the value of charge remaining on the capacitor will be 0.37 Q, that is 37% of the initial charge will remain there on capacitor, or we can say 63% of the initial has been discharged within the duration of its time constant. But the most important thing is the time relation of a charge as a function of time when a capacitor discharges through a resistance R. So be careful about this result. Here also we can say that approximately after 5 times the time constant, the capacitor will be almost completely discharged or discharged up to approximately 98% of its initial value, and remaining 2% can be ignored as it will take almost infinite time to get discharged. So the transient duration will be again almost 5 times of the time constant. Then onward, this will be the steady state of a circuit when current drops to almost 0.